So in this film about how to compute limits for sequences in practice, we're going to look at the squeeze theorem. So what does the squeeze theorem say? It says that if you have three sequences, an, bn, and cn, and you know that the ans are always smaller than the bn's, who are smaller than the cn's, and that the ans tend to L and the cn's tend to the same number L, then this has to hold for all the n's. These things together imply that the bn's tend to L as n goes to infinity. A detail here is that we're not from the start assuming that the bn's converge themselves. So the fact that the an's and cn's both converge to the same limit implies that the bn's converge, and they converge to the common limit of the an's and the cn's. If you want to do a drawing of this, then well, here perhaps you have your cn's. This would then perhaps be your L. Here you have your an's like this, and then your bn's. Well, there's something that is captured or squeezed between these two sequences here, and therefore also have to converge to L. So the squeeze theorem has many names. So it's the policeman theorem, or it's been told to me that in the Soviet Union they call this the KGB theorem. In Swedish you call it the instängningssatsen. And this is a very useful little result. So let's see an example of why this is. So let's consider the limit as n tends to infinity of sinus n divided by n. So as with a lot of other limits we meet, then the actual result isn't that mysterious. So sin n varies between -1 and 1, while this n here tends to infinity, right? This means all of this has to be crushed down to 0. But how to prove it? Well, the squeeze theorem gives us a nice little way of doing that. So the first thing to notice is that sin n, as we said, is always between 1 and -1. And if we divide by n on all sides, we get this thing here. So now the sequence we are interested in is squeezed between two other sequences that both clearly go to 0, and which is basically part of our rule book for the limits. And now my way of kind of formally writing down proofs by squeeze theorem is that I would say that this tends to 0 as n tends to infinity. This tends to 0 as n tends to infinity. And then I write my little box here and I say squeeze. This will then tend to 0 as n tends to infinity. Hence, as we were supposed to prove. And we're done. So the advantage of the squeeze theorem is that in studying something that has a fairly complicated behavior, we're able to kind of get rid of the unnecessary complications. So what sinus n is horribly complicated. It's if you go to Python here and do a for loop, so for n in range 0 to 10, print sin n. Of course, this won't work, so we'll do np sin. So we need to get the sine function from the numerical Python package. And now we can print this. And you see all of these weird numbers, right? If I put a pi here, so pi n, then I would get it. But what sine does at n is actually quite complicated. So this is a quite complicated expression, but the complication is irrelevant, right? The only thing we care about is the fact that sine is between -1 and 1, and that we're killing this by dividing by the n. So similarly, in other situations, if we have a limit where we can actually take away a lot of complications, then it could be that we can determine the limit by using the squeeze theorem. And we'll see this on several occasions.